In the first place, I want to welcome everybody that's come on the part of Alan and myself and the GBC group. And I'd like to say that this is really, for us, a very encouraging moment. When we had our last meeting in November of the year past, not last one before, we were still getting out of the pandemic, activity was starting, we had results, but I have to say that during this period, everything has become much more lively. And therefore, what Alan and I decided was, instead of having a more formal meeting to discuss different projects and work groups, we were already ready to be able to have a scientific session. And I'm sure that the future ones will be even richer. So the program has been established to highlight the scientific advances of the GBC community. So I'm going to start my short presentation. Here I'm going. And well, this is going to be a welcome and an update about the GBC meeting. And after me, Alan will continue. And what I have to say here is that let's see, next slide here. Okay, what is the GBC, the Global Brain Consortium? It's an organization that follows the principles and practice of democratization of brain mapping, and including all countries. We have an emphasis on low and middle income countries. There you see the first meeting, which was in 2019 in Montreal. And you can already see the level of participation that has only grown. Our projects are collaborative neuroscience initiatives that increase access for low and middle income countries. We have an emphasis on neurophysiological data access standards, and it's not exclusively on this, it's also multimodal imaging, neuroinformatic methods, and infrastructure. And best practices for open science in the international arena, and potential applications for disease disorder discovery or equitable global mental health. We have a steering committee. Here you see, besides Alan and me, we have JB Pauline, Catherine Ammons, the European Brain Project. Marianne Manton represents the INCF. Paolo Rossini represents the International Federation of Clinical Neurophysiology. We have Jane Roxham that says UBC, but she's actually now at the Child Mind Institute. Bartha Knoppers, Paul Thompson, who is leading the Enigma project, Greg Farber from NIH. We have Dejong Yao from China, and we have Michael Milham, who we will be hearing from later. The GBC has this steering committee, but it also has a project executive committee. We have projects for global EEG norms, for COVID-induced brain dysfunction, for the neuroscience of brain development, for biomarkers of Parkinson's disease, and for biomarkers of Alzheimer's. We will be hearing scientific results from all these projects as the program advances. We have a close relation with the World Health Organization, with the Division of Mental Health. In fact, the GBC was spawned by a meeting of the Global Brain Projects at Geneva at WHO headquarters. You see the photo there. And here, what we're doing was recognized as something needed that we address with our neuroscience research, the global burden of brain disorders. We've had continual guidance and participation with the creation of a novel brain health unit that didn't exist at the time of the meeting. And to give an example, very soon, 2/3 of May, there will be a world meeting where the GBC has been invited to discuss current efforts to measure brain health in early life. I will be representing the GBC, as will Damien Fair, for the Global Longitudinal Child and Adolescent Development Project that WHO asked us to put together, and Jorge Bosch for the GBC. And this is an example. We were asked to do this that we call in short the GLAD project for longitudinal studies, and we will be giving our input to WHO continuously. Since our last meeting, this is quite new, we have now established an alliance with the International Federation of Clinical Neurophysiology, very briefly. It has 62 societies in 58 countries, more than 20,000 members. And what we have agreed upon, having Paolo Rossini as the liaison, to work together so that what we're doing in EEG infrastructure, software, and research actually engages the people that are using these tools worldwide. This was one of the symposia we presented. You see, it's about quantitative neuroimaging in Latin America, with examples from Latin America, also aspects of cloud computing. Now, another very important addition to the GBC has been the work of the Child Mind Institute. I won't speak about this. Alan and Michael Milham will explain this. And I have to say that we have now also working with us a very interesting project, which is born in Bradford, which has been following, as you see there, for decades, since children were still in uterus till now. And they have many different types of assessment. And now we're coordinating because they're going to start EEG. We'll hear about that also at this meeting. This is precisely the project, which is part of our efforts, which is replicability of influential EEG experiments. I've already mentioned and won't enter the detail that one of the first outputs that we have are harmonized multinational QEEG norms. This was led by Ming Li, the main author of this 9-country gathering of data and analysis to produce harmonized EEG norms. This is in the public domain. I've explained this before. I just do want to mention that now, both in Montreal and here in Chengdu, we've established the basis to have mirrors of data to be shared in different degrees, depending on the agreements we control. The one we have here in Chengdu will be extensible to 1.6 petabytes. We are also going to explain the work of the GBC. I have to say that there's going to be a local organizing committee symposium in, this is coordinated by Julien Doyon, and Alan and I will be talking about the work of the GBC, okay? Now, I go, because I want to keep my presentation short, some organizational aspects. First, you can tell your friends who are interested and were not able to be here that we will be either streaming or later playing this on YouTube. This is for the streaming. This will differ in some time because we will have to record and then put on YouTube, but that's all right. Those that haven't Zoom or haven't registered on Zoom, there are the links for the different days. We will also organizationally, I have to mention that we have an organizing committee. Jorge Bosch, Arioski, Michael, Mikey, and Christine have been invaluable. I really want to thank them for the effort they've done in organization. And we have, for each of the sessions, 2 people, a moderator and a technical assistant. If you have doubts or anything or want to upload anything, you just pick your moderator and then you can write to them. There are the emails, they're in the program also. The latest version of the program has been put into the chat of this Zoom, but it's also on the webpage of the GBC. If you want more details about the GBC, please stay tuned to the YouTube videos and also to the webpage. And this is it. I hand the floor to Alan Evans.
All right. Good morning, everybody. It's a pleasure to welcome you all to the annual meeting of the Global Brain Consortium. You've heard the specifics from Pedro, so I will not repeat those comments. We thought it would be helpful if I provided a brief overview of some of the larger context within which the GBC sits, to give you the sense, the understanding that there's a lot behind the GBC curtain. Specifically, The Global Brain Consortium is a brainchild of the Ludmer Center for Neuroinformatics and Mental Health, particularly our sponsor, Mr. Irving Ludmer, who you'll hear from shortly. Also, a large component behind the curtain is the Healthy Brains, Healthy Lives initiative at McGill. This is a large project to create a global center of excellence in neuroinformatics and translate discoveries into brain health. As you can see, over 200 PIs are involved in this large enterprise. And the overarching thrust of HBHL is to understand brain organization at a network level, a systems level, as well as a molecular level, and to essentially take a big data approach to neuroscience questions in neurodegeneration, neurodevelopment, and normal brain cognition. Underpinning all of that infrastructure are two major platforms: the LORIS multimodal databasing environment that allows us to capture imaging, genetics, epigenetics, behavioral data, biospecimen information, electrophysiology, and on the other side is CBrain, the portal to the high-performance computing infrastructure, originally of Canada, but now we're incorporating a number of sites internationally into the CBrain network. So this infrastructure underpins everything that we're doing within the GBC. A little bit more detail on the CBrain story. CBrain, as you can see, originally captured 7 HPC sites across the country, but now it incorporates the Texas Advanced Computing Center, San Diego Supercomputing Center, the Pittsburgh Supercomputing Center, as well as European initiatives, as you can see, eBrains and Surfsera. So there's a lot of global interaction mediated through CBrain. CBrain at this point has over 1,500 users internationally in 32 countries. And it provides analytic tools. Over 100 different workflows are at this point available through CBrain. In the Canadian context, many different projects are supported by this infrastructure that I just described, and I'll only hint at one or two of these as we go on. The Canadian Open Neuroscience Platform, as the name implies, is an environment to support data and tool sharing across the country, training, ethics and data governance, policy, documentation. And at this point, CONP has made available approaching 100 different pipelines and over 70 different data sets of various kinds. You can go to the CONP portal to explore that in more detail. Also underpinned by this infrastructure is the CBIG Clinical Biospecimen Imaging and Genetic Repository, a biospecimen repository here at the Neuro. And that's got data from, at this point, 3,000 subjects. And you can get access to all of that tissue in an open capacity. On the international scene, there are many different projects which are supported by this infrastructure. I'll mention, for instance, the Highball Helmholtz International Big Brain Analytics and Learning Laboratory. And Highball is essentially a project to explore AI applications in neuroscience and to build an international interoperable platform across Europe and North America. It's originally based on the Big Brain dataset, which I think many of you will be familiar with, and I won't dwell on this beyond saying that this is a very large-scale data processing environment. Importantly, the group is now beyond just the 2 original sites. There are over 400 researchers in 41 countries involved in the Highball network. And the Highball network is made up of 6 different work packages. Most salient for today's discussion is work packages 4 and 5, where we, first of all, we have built an infrastructure to allow data sharing in a transatlantic capacity between our European colleagues and the North American colleagues. Data can be sitting in one side of the Atlantic and processed using the pipeline that I described on the other side of the Atlantic. Bratislav, Mizik, and myself are heading the virtual Big Brain project, but this is actually a cost of thousands, including Pedro Valdez Sosa, very specifically, where we're exploring the applications of electrophysiology, EEG, and MEG in an expanded model of the virtual brain, making use of the big brain data that I just hinted at. On the Canadian side, but also with international linkages, is the EEGnet platform. And as the name implies, it is a network of researchers across Canada and our international partners who are engaged in EEG-based research. And Pedro and Scott McKay, Kay Robbins, Arnaud Delon, Cyril Penday, and Claudia Babylonia are very active within EEGnet, along with the Canadian partners. EEGnet's goal, as you can see here, it started in 2022, is to develop a platform for expert annotation, open toolkits for curation and BIDS annotation, the release of annotated EEG BIDS data, and accelerated EEG analysis pipelines. So all in all, this is an environment to develop a unified platform for sharing and analysis of standardized EEG data sets to the national and international communities. Recent relevant developments within EEGnet and the GBC are new analytics pipelines that are online in CBrain. And we've developed a harmonized multinational quantitative EEG norms toolbox, which you'll hear about from Jorge Bosch-Bayard, an EEG signal browser, and then implemented support for community-driven standards. We have a conversion for a setup and the formatting for EEG BIDS support, the hierarchical event descriptors from Kay Robbins and Scott McKay, as well as a clinical EEG ontology from Sandor Benici, Dora Hermes, and Tal Attia. And finally, an EEG to BIDS converter that we've developed. So I've given you a very rapid Cook's tour of related projects which all combine to underpin the Global Brain Consortium. You've heard from Pedro already in the details of the GBC. I'll now just post a small video from our sponsor within the Ludmer Center, Mr. Irving Ludmer. So if you'll indulge me in a second.
Good morning, everyone. It is a great pleasure to welcome you and see the Global Brain Consortium growing and moving forward with this meeting. I wish I were able to shake all your hands in person today. The GBC's impressive activities represent a perfect example of the ultimate objective we had in mind when we created the Ludmer Center for Neuroinformatics and Mental Health, supporting a global research ecosystem, fostering collaboration that can be leveraged to address inequities in neurological and brain health challenges worldwide. Today's growth of AI and machine learning, even to the point of adding organoid intelligence, will see biology and neurology rise to greater and greater heights. I am most proud that the Ludmer Center is able to contribute to some of the next great endeavors of the consortium, demonstrated through new projects and ongoing initiatives such as EEGnet. I want to thank our friend Dr. Pedro Valdez Sosa and his team for organizing this event, as well as the team of Dr. Alan Evans. I am convinced that even more exciting research opportunities will emerge from the talks and discussions this week. I also want to thank Dr. Michael Millam for presenting the Vera Gross public lecture. We hope to create an annual venue to showcase innovative and interconnected global brain research. Dr. Millam's talk on expanding horizons in electroencephalography, health applications through technology, is certainly a fitting illustration for this tradition. Thank you all for your participation and have a great meeting.
So it now falls to me to introduce our guest speaker. This is Michael Milham. Let me just give you just a few comments about Mike. There's a lot to say, but I'll just try and cover it briefly. Michael is an internationally recognized neuroscience researcher. He's vice president of the Child Mind Institute in New York. is founding director of the CMI Center for the Developing Brain. In the past, he's also the director of the Center for Biomedical Imaging and Neuromodulation at the Nathan S. Klein Institute for Psychiatric Research. And he's at the New York State Office of Mental Health. I could go on, but there are many other opponents. More importantly, Michael his research on is worldwide on functional and structural connectivity that may underlie mental illness. He's working on brain development in healthy and affected children, and in general, a big data approach to brain research and open data sharing. He co-founded the 1000 Functional Connectomes Project. He founded in 2010 the International Neuroimaging Data Sharing Initiative, or INDI. And under that umbrella, we've had very large number of data sets which have been shared to the international community, including the ADHD 200 data set, the ABIDE Autism Brain Imaging Data Exchange, the Consortium for Reliability and Reproducibility, the Rockland Sample, and the CMI Healthy Brain Network, which will eventually include 10,000 participants. He's published over 250 articles since 2005 and is a highly cited researcher since 2014. And he was the OHBM's Wiley Young Investigator in 2014. So with that introduction, let me hand the talk over now officially. This is the Vera and Mortimer Gross lecture. We're very happy and delighted that our sponsors have allowed us to support this initiative in this talk. And Michael will talk on multimodal characterization of brain and behavior, the last missing ingredient for precision neuropsychiatry. Over to you, Michael.
Okay, thank you, Alan. First of all, thanks for having me, inviting me to talk at this meeting. It's an honor. And the title, I will say up front, no, it's not the last missing ingredient, but it is a big one. And I will kind of go through my thinking of this and start with what, if you spoke to me months ago, I would say, or years ago, say is less missing ingredient, but you'll see an evolution of the thinking. And with that said, before I get started, I just wanted to acknowledge no commercial relationships to disclose. So, okay, let's start with precision psychiatry or neuropsychiatry. What are the promises? So we look at the promises, they've been relatively steady over the years. First, this vision of redefining psychiatric nosology in terms of neuroscience, and this thought that we'd be able to look at the data in order to try to delineate valid boundaries between different subgroups or clusters within psychiatric illness. Next, of course, has always been the talk of bringing objective measures of illness to clinical practice. So there, whether one's talking about determination of presence or absence of illness, staging of illness, risk, prognosis, monitoring treatment response, this has been a repeat theme. And it's not surprising given that mental health is really the last frontier of modern medicine that lacks objective measures of illness. And then, of course, the ultimate of precision medicine, that idea that we'll be able to sit there and stratify folks in order to figure out what next step makes the most sense for this individual. When would we expect a medication or any other intervention to be more or less effective based upon the individual, not just based upon some profile of a one-size-fits-all style approach. And in more recent years, we've seen an increasing number of calls for guiding interventions, brain-based interventions such as TMS, which honestly, when you look at brain imaging and where its first delivery would be, I really think the most direct deliverable probably is actually the brain-based therapeutics front. When we think about TMS, we already see folks like Mike Fox, Connor Liston helping to lead the way in thinking through applications of imaging in TMS and using it to optimize targeting. That I think is probably the most readily accessible application of imaging in psychiatry. That would probably be in my mind among the first that will be most scalable, and then those others can follow. And as far as is all this feasible, here's just a small sampling of papers pointing to the ability to improve prediction, pointing to, in order to produce, to identify subgroups of populations, whether on an autism spectrum, ADHD, or so forth, that aren't appreciated in DSM. But when we infuse knowledge from the brain, we can get there. On the flip side, it's no secret, we're not there. And that's something that, I basically started on this hunt probably back in 2004, 2005 during residency, when I went to NYU and joined Javier Castellanos' team, and really started thinking, especially once we stepped into resting state fMRI, and really saw so much potential for developing biomarkers, which would bring us to about 2006. Something that seems so distant on the horizon, resting state fMRI and some of the advances that were going on at that point made it really more tangible. And it got me really thinking, what are the properties, going back to laboratory tests and going through that thought process. And now if I look at it, I guess more than 15 years later, we're still not there, but I actually think we've made huge progress. If you asked me then, I would have said probably about 40 years. Now I'm down to like only, 10, 15, 20 years. So I think the gap really has decreased and continues to decrease between us, where the field is and where we're trying to get to. With that said, it causes me to repeatedly revisit in my mind, it feels like on a way too frequent basis, what gets in the way. And what I was referring to earlier is one of the most consistent concerns has been reliability. This started back in about 2008 or so, when we were first getting very excited. I remember Javier Castellanos and myself were sending a grant submission, specific games from grants that we were working on to Don Klein at the time, who basically looked at it and said, anything this robust as what you're saying is resting state is probably either a biological artifact or not really that meaningful. And so he said, can you get retest reliability for this? And that actually prompted our early work in looking at retest reliability and saying, can we get reliable individual differences? And there were some encouraging results. And then also in years later, we realized some networks in the brain we were, some not. And that began really this focus on reliability. It was really Don Klein's prompting. So why do we care so much about reliability? First of all, going back to just core, what we know for anything that you hope will be a laboratory test of any form, is reliability is one of your core criteria. You have 4 core criteria between validity, reliability, sensitivity, and specificity. And then you also have that caveat of, even if you meet all those, is your method going to have a widespread availability? Reason why we focus in on reliability so much is because it does represent the upper bound for validity. Some folks I know now are saying, well, just look at validity, just look at validity. Well, that's a very complex challenge in the absence of ground truths. But also, if you don't have reliability, you could be rest assured you will not have validity. It is an upper bound. And so that's why we put a significant focus on that. At the same time, it's also important to realize it's necessary but not sufficient. You could be reliable, but you can have a reliable artifact, a reliable contaminant. That's where validity becomes so important. And the thing is, in a time where everyone's been focusing on sample sizes, there is a reality that we can't escape, which is reliability is one of your major determinants of the sample size needed to detect a given effect. So if you want to not have to be required to have incredibly large samples, then you really need to increase the reliability of your measurements. Now, even though I'm going to be talking about multimodal characterization eventually, I'm starting here because you got to think about first, for any modality, that you need to think about optimizing reliability. Because if you haven't, then you're just trying to cover up a larger problem. And this is true. While structural imaging probably boasts the best reliabilities, if we look across the board, there's a whole range of reliability concerns that affects most measures, not just fMRI, even though as an fMRI investigator, that's what I worry most about. But EEG and others, and also aspects of structural we have to be careful. Even if we think that one measure is reliable, one feature is reliable, we change the feature, we might be stepping into something that's not reliable. And we don't actually, if we're not looking, we don't know. And the challenging with any of the communities is there's a tendency not to look. We get so excited by the next idea that we step away from those basic tenets. That actually, I'm sorry? Oh, okay. We step away from those basic. We step away from those basic tenets that we just can't escape. And I'm just highlighting this as a recent paper that we had put out just for a functional MRI and specifically that has a lot of these ideas in it. If someone wants to read more about the big picture here that I'm going to be discussing. Okay, so fMRI data. You know, here, and using this one as an excellent example, what have we seen in the last 4 or 5 years? We've seen a number of papers, whether it be functional connectivity, task activation, raising concerns about reliability, looking at the literature and saying, you know, what are we actually using? Which it's important to have these reality checks, especially when it comes to something so fundamental. At the same time, particularly in the resting state fMRI or functional connectomics front, there actually has been great progress. A number of studies have really taken on the challenge of looking at what are the minimum data requirements. And I remember back in 2007 and 2008, the big sell on resting state is add 5 or 6 minutes to your study, and that's all you have to do. Just stick it in, and you'll get all this extra data. And that's how the field thought. Now folks realize, wait, you need notably more data. You probably want 25, 30 minutes of data. And the thing is, with that 5 to 10 minutes, what you typically will see is when you're looking, if you're looking at the frontal parietal network, the fault network, you will do relatively well. But then you have to worry because you have a literature where there's so many associations with frontal parietal and default networks. So is that really because those are the most prominent and important networks in psychiatry? Or is it just that that's where we actually get the most reliable signal? And then, of course, when one looks at this, there's a growing number of features. So here's an example where connectivity gradients have become particularly popular in the imaging literature following the initial work by Daniel Margulies. And here's a paper where we did is we looked at what if you have 5, 10, 20, 30, 40, 50 minutes of data, and you just get a steady ramp up in your reliability as you increase the amount of data, and not surprisingly, that turns into more greater detectability for brain behavior relationships. So again, if you go back to the basics, this is all predictable. But then if you look at how we so often behave, we step away from those basics in favor of innovation, which is understandable at several levels. But we at some point we have to address this. And this is often I can say, out of all the grants I've gotten in my career, I've never gotten one on reliability. I've never gotten one of those through a study section. Because it doesn't sell well. It's a fundamental, but it also lacks a certain appeal to folks. And that's something that I think as members of community reviewers ourselves, we really do need to give greater attention to issues of reliability. And then, and so on the one hand, my mind, test reliability, immediately solvable. Of course, whether it's be able to keep increasing amounts of data or what Connor Liston and others like Damien Farah are now advocating, which is putting more of a focus on multi-echo, which multi-echo imaging or multi-band multi-echo imaging, which really seems to bring down the data requirements for achieving more reliable data. One way or another, that we can solve. And then, of course, comes inter-scanner reliability. Again, here, this should also be a solvable problem. We have a tendency to have very limited human phantom data sets. And when people often think of human phantom data sets, they don't really think about having data sets that are large enough to look at the stability of individual differences. They often look at the stability of the individual, which if you just measure one individual across multiple scanners or very small number, you're going to detect differences. But how much does it impact individual differences, the stability of the differences detected from one scanner to another, and really being able to have those data sets available to optimize? That is still not, they are still not present in the community at the level that they should be. And that will hold us back. But once again, imminently solvable. Another challenge in reliability comes down to actually the analysis pipelines and decisions. And there have been a growing number of papers raising these concerns. And again, when it comes to a concern that cuts across all of neuroscience, this is one of them. I'm going to focus in on functional connectomics as in this example, but this here, there are very few areas of neuroscience that could really say that they could step up to this challenge right now and be sure to have enough standardization to have reliability between pipelines. So here's a preprint that we put up a year or so ago. We actually are just now revising the manuscript to go back into the publication process. One of the things we encountered is folks, as I was saying earlier, this confusion between reliability and prediction, or validity, or predictive validity. So we're working now to just very clearly make it obvious that predictive validity depends on reliability. In this work, what we had done is we basically took 5 different pipelines. At broad brushstrokes, we just looked at their minimal pre-processing. 5 different pipelines, each do denoising, brain extraction, tissue segmentation, anatomic registration, slice diamond correction, so forth. And the thing is, at face value, they're all doing the same steps. These are all minimal processing pipelines, or portions of minimal processing portions of larger pipelines. But you'll notice that they each use different components to accomplish those steps. So there's actually not all that much in common with the specific algorithms being implemented across the pipelines. You can come with a variety of different settings. So the first thing we did is we took an openly available data set, the HNU data set, or Hangzhou Normal data set, a university data set from the Consortium for Reliability and Reproducibility. And we ran the 30 subjects of data through each of these pipelines, generated connectomes. And we asked the question, well, what's the reliability? So it's the same data from same subjects. And here what you're seeing is same data from same subjects put through different pipelines. Ideally, you should see ones, whether you're looking at the correlation of the matrix produced for a subject between the different pipelines, or if you're doing edgewise ICC, looking at individual differences. But again, it's really actually just across pipelines and a more multivariate approach. So using I2C2 or discriminability. So, but you're not seeing ones here. Instead, you're seeing with the same subjects, same data, I get patterns of individual difference that are actually quite divergent, so notably compromised. Right here, you'd like to think at least 0.9 and up, maybe 0.8 and up, but in many cases, you're seeing it comes down. And then, of course, it depends also on how we represent the brain. Are we using a lower resolution or higher resolution? This here is a significant warning. When we talk about a field with reproducibility crises and so forth, and a field that wants to move from group level inference to inferences about individual differences, and of course, going through subtyping and so forth, this here is something that needs to be addressed. So what we had done in this work is we then using our pipeline, the configurable pipeline for analysis of connectomes, or a CPAC, we basically, a CPAC is designed so that it's highly configurable and you can iterate over a range of different pre-processing decisions. We basically made it extend its configurability so that we could replicate all those other pipelines in a single package. And then we went back and said, okay, so if you actually use a pipeline that's harmonized in CPAC against the ABCD bits, for example, now all of a sudden you can achieve high inter pipeline agreement. The thing is, that requires a concerted effort. It took a significant amount of work between groups to even understand the nosology, like our nomenclatures, the way we think about things, all that whole process we had to go through with each of these pipelines in order to achieve that. Once having achieved this in a single configurable pipeline, we could also then start asking questions about what steps contribute to this variance. The challenge is, one of the things you wind up seeing is what steps contribute to variance between two, or differences between two pipelines varies depending upon which two pipelines you're seeing. So it's something that can be worked through and solved, and again, standardization, graded collaboration can make happen, but it's actually an incredibly large challenge ahead, and it pushes for the need for not necessarily standardization where we all need to use the same one-click pipeline, but we at least need standards and references, pipelines, and ways of comparing to one another in order to be sure that we can have meaningful examinations of individual differences. And, here going back to how do you put all this in perspective? One of the things we didn't want to do is have this become this salacious, the field is in trouble, everything's on fire style papers. So what we did is we looked, if you took the same subject, same scans, so same exact data, same pipeline, you get beautiful reproducibility. Putting it through different pipelines, what you're seeing is here is the different compromises in reliability, like I was showing earlier. Now, so that's the upper bound of what you're going to get. But when you have, the thing we then did is said, let's look at test-retest reliability. So same subjects, different scans. The reality is where the field is at with the reliability of the data it's been using, you're not really hitting that upper bound yet because the actual data quantity is too low. So I guess the point is these differences exist in the literature. It's a source of variance. It will bound us more when we really start using our highest quality data. With all the other sources of variance, these pipelines are there, but they're not our current upper bound. They're becoming our upper bound as we improve our data quality. So it's not to say that we should be mortified about everything past. It's really a warning about as we're going forward. As we improve the data quality and we solve that problem, we have to think about our pipelines. Just a quick plug here for the NMIND Consortium. Greg Kerr, Damien Fair, myself, Satra Ghosh, Russ Poldrack, Ted Satterthwaite. I started this some time ago. There's a website you can go to. The point of this consortium is really it's a collaborative focused on trying to bring alignment between different groups focused on pre-processing and different forms of analysis, and really working through alignment, working through how to evaluate software and trying to engage community. There are monthly hackathons. There's a commentary right now under review for this. There's a website, you can read the white paper and so forth. And if you are interested in getting involved, just reach out to us. So, okay, I said I was going to, the start of the talk was about multimodal characterization. So where does that fit into this picture? Because I've been talking all about reliability and single modality. Well, when we think about multimodal, these are classic images. You can find 1,000 versions of these images, really thinking about the different tools at hand, essentially, for looking at brain function. And when I think about as opportunities for multimodal imaging, things that start to jump out in my mind are establishing validity, complementary perspectives and features you can get from the data, and translation between modalities, which can be important, especially when you're thinking of something very expensive and less accessible like fMRI and versus something like EEG. And that potential, can we translate between? So historically, historically, when I first ever started thinking about multimodal, it was really truly validation. If you were a resting state fMRI researcher in the mid 2000s, late 2000s, your biggest thing is to be called looking at anything other than an artifact. This here was work by Steve Smith that I thought was a beautiful piece of work, which really showed here's still fMRI, but two very different forms of fMRI, task and resting state, and being able to validate those patterns of resting state against what you get from basically applying ICA to task fMRI. And then here's another example, resting as now we're going a bit more distant, which is what you really want when establishing validity. So resting state fMRI versus MEG. And here's examples of works where folks were basically helping to establish the validity of resting state fMRI by looking at MEG and deriving networks in connectivity networks from MEG. And this is a collaborative effort that I was fortunate enough to be a part of. Now here going more looking intracranially and looking at cortically evoked potentials and verifying that their path follows that of connectivity networks from resting state fMRI. So these are examples, and there are others using ECOG and so forth, where we can sit there and really think about multimodal as a way of validating our tools, which is incredibly important because there's so many things that you really need to be more invasive with in order to really validate and or to optimize. And that is one of the things that multimodal gives us. Another aspect of multimodal is really this idea to get complementary features or establish complementarity. So this is work with Lucas Parra using the Healthy Brain Network data set, where basically we looked at functional connectivity patterns based upon fMRI and based upon EEG. And this is looking at source localized EEG, and basically establishing that just as with resting state fMRI, you can get individual specific patterns of connectivity, but they're not equivalent between fMRI and EEG. And you can even find variation, of course, depending on which band you're looking at. What this points to is, this is just one of many examples, is the fact that there's complementary information, which that should not be surprising. But we had, the field is just beginning to think through leveraging the value of such complementary information in order to really best inform our understanding of individual differences in the brain. Here is an example of a paper where, now staying within modality, with just structural imaging, we basically looked at improving brain age prediction by combining cortical thickness, geodesic distance, surface area, using an approach called joint individual variance explained, or JIVE, and basically try to establish the value of going more multi-feature rather than having yet another study that chooses some feature of structural imaging in order to do brain age prediction or other approaches, so that we each have a different feature that we're saying is great, instead looking at the joint variance and also taking into account the individual variance and pushing forward. Now that's all within structural imaging. Then we have work like this here, which when I saw this paper in eLife, I just thought this was a beautiful demonstration. Here, what they're doing is taking MRI, fMRI, and MEG, and what they're doing is brain age prediction, but they're applying ensemble learning, and they're using an approach referred to as opportunistic bagging, where it's at the first level, it's ridge regression, second level, it's random forest regression. And so you use the ridge regression within modality, and then you use random forests to basically ensemble across modalities. And and then the opportunistic stacking part is where they basically allow for missing data, and the missing data basically gets devalued in the models in the random forest. All this basically comes to show that they improve brain age prediction, but also were able to improve, showing that deviations between expected brain age for an individual and actual, someone's actual age and the predicted brain age could be related to parameters like depression, like cardiovascular fitness, fluid intelligence, and they're showing an advantage for having multiple modalities. Again, that's this example of leveraging the complementary information across modalities. And here's just examples of a growing number of papers that I've been finding in recent years, looking at combining structural and functional connectivity and structural measures, and showing the value of multimodal brain imaging, and bringing together multiple modalities, so that we don't just be, I'm a functional connectivity person, I'm a structural connectivity person, each person having this competition about who could push their method the most. But instead, we know there's so many data sets that have now functional and structural connectivity. All data sets that are fMRI typically have a structure to go with them, so you also get the structural features. We know that there is this ability to combine the data, but it's about pushing the methods forward to make that easier. To do good structural imaging takes a lot of work. To do good functional imaging takes a lot of work. And so it's understandable why we so often focus on one. But we're reaching a point where we do have increasing number of pipelines that can automate the process. We have increasing amount of knowledge to bring these different modalities together. And again, as I was saying, it's great to see that for multimodal imaging, but really combining imaging and EEG or MEG, that is really the next major step that so many of us need to do if we really want to get more complete perspectives of brain function or organization structure. Another thing I'd mentioned was translation between modalities. And this here, this work is giving examples by Tom Handler. This work with the EEG fingerprinting I found very appealing. And what I loved about this is they took an initial finding from back in 2014 as far as their ability to develop scalp EEG fingerprints of fMRI activity in a deep region like the amygdala. And so that you're able to basically train on a simultaneous data set, get your scalp-based prediction model, and then remove the fMRI component of it, and use EEG to now, and EEG models that are trained to predict activity in a particular region, the way we would think about it from fMRI, take those models and apply it in this example in a neurofeedback training approach. So that, and it was funny because when I first heard about this work, I first heard about the EEG neurofeedback training, and my usual skepticism kicked in. And then I noticed where it was published, and I started looking at the size of the sample, and then I started going through and learning about these methods, and I was just incredibly impressed, because I do think that the idea that how do we translate from imaging to more practical, scalable approaches such as EEG. I think this here is just an excellent example, and one that there are others, but this here, it's a nice story when you look at the work they've done. One thing that I'll point out is this here is, I think it highlights just one of the last things I'm going to drive home is we really do got to think about, so here, this is a paper by Suk-Jun Hong, Adrian DiMartino's review about subtyping in autism, neurosubtyping in autism. And when they looked at the literature and the papers that were trying to start doing neurosubtyping, you see the challenge. Whether the features one's using to subtype or to validate, there's a range of methods being used, and it needs to come together. The way we can come together is we're going to not need to have EEG on this set of subjects, fMRI on this set of subjects, structural on this, but we need these multimodal data sets that pull it together. Now, I'm going to finish up the final segment by focusing on going beyond just brain, looking at brain and behavior when we talk about multimodal, because everything I just spoke about was multimodal brain function, multimodal imaging. But when we think about multimodal characterization, and really I should say brain and behavior, well, this starts off there was a meeting in 2016 that NIMH hosted for RDoC, which when I found this paper online, or the outputs really in white paper form, and you can find this on the RDoC website, it was instructional. What they were trying to do is they were trying to identify tasks to recommend as behavioral cognitive probes for RDoC. And when you actually look at the document, they did their best, but the document it really brings forward the limitations of the field at the time, which I would argue are still present to this day, though improving, which is they couldn't really find a set of tasks for which reliability was actually good. I mean, when you go through so much of their appendices, you look at the different RDoC domains, you either see people haven't established test-retest reliability, or you would want a 5, and instead the ratings are 2 or 3 or 1. What this highlights, and actually this is very nicely done as far as if you look at the many different things they were asking also about longitudinal stability, practice effects, used across different sites, so it's scalable, can be used with children, special populations, and so forth. But right at the beginning, when you look at this, you're in trouble. You basically are trying to recommend behavioral probes for a field where so many of when you look at cognitive neuroscience, so many of those tests were designed to really give us group level inferences about brain function. They weren't designed from the beginning or optimized in order to figure out what's the true data requirements in order to establish reliable differences among individuals. And it comes through. They weren't tested, or we're using tests that when you go through their grids, a lot of very popular tests have relatively poor reliability. And then the funny part is you then think of it, then we're going to go compare that with functional imaging. And so now we're going to have tasks that have poor reliability behaviorally. We're pairing it with functional imaging, which has its own reliability issues. What are we going to wind up with? And another challenge that this Jim Swanson some years ago put me onto, that I also see playing on the literature, is that when we take scales designed for mental health in clinical populations and we put them into studies, especially if we're putting them into population studies, what we will get is how pathologic is an individual. But we will never get what strengths an individual has. The challenge with that is for any given scale, what you're going to get, unless you have a very pathologic sample, is you're going to get these truncated distributions. And if someone just looked at a truncated distribution and said, is this a wise thing to go and relate to my MRI data? You would say no, and that was Jim's argument back then: is why are epidemiologic, genetic, imaging, all these different fronts using these scales in populations that are not that are transdiagnostic or community based, when they're not designed for that. And instead, what you have, it's basically like wanting to look at IQ and capping IQ at 100. So everyone above 100 is the same. Everyone below, well, there could be variation. That's how we wind up treating psychopathology in so many of our measurements when we do this. And in this paper, we suggest alternative approach based upon Jim Swanson's approach, something called the eSwan, where we wind up looking at differences in scale construction to actually create a symmetric distribution. There's a number of ways of addressing this challenge. But the bottom line is, this is what we're going and relating to our imaging data. So if we stopped and thought to ourselves, wait a second, in some of these cases, 50% of our data may have no variance. And then what's that going to do to reliability of your behavior measure? Nothing good. So then when we see findings, and like example on the left is the Hong paper from our team I mentioned years ago, on the right is the Maverick paper, where what you see is psychopathology does so much worse than something like cognitive ability. The bottom line is it should. If you're looking at ABCD and you're saying the CBCL, or you're looking at Human Connectome Project and you're saying the adult self-report, these are population samples for which a very significant portion of the population does not have psychopathology. So you have zero variation. So how will you expect to do well in basically indexing variations in brain behavior relations? It doesn't. From that perspective, of course, we expect measure NIH Toolbox and other indices of cognition to do better. And this is one of those parts where, the thing that scares me is then when I hear people say, well, psychopathology, you're not going to pick that up so well in the brain. It's more complex. No, it's not being measured appropriately. We don't have the best measures to do this. And we're confusing two issues. Here's a preprint that right now is currently under revision. It's led by Aki Nicolaitis, where Aki tried to really draw attention to the challenge of joint reliability, and really driving home that when we think about reliability, you can have if your brain, you can have very reliable imaging data, like what's easily attainable with structural imaging or with higher, more dense sampling of function. But it doesn't matter if the reliability of your behavioral measure is low. So as we keep focusing on optimizing reliability for the brain now, and the community has put made that more of an agenda, if we don't better accomplish that for the behavioral measures that we're using in characterizations of psychopathology, then the bottom line is that joint reliability is what governs our success, and the joint reliability will remain poor. You need to balance both. You need to optimize both sides of the equation. And that's something that this and some other recent papers that I've seen emerging are really trying to drive home to folks. So for the last part, I will talk a little bit about, a key challenge in all of this is we need to be creating the data sets that can be used for multimodal characterization exploration. That's not easy. It takes a lot of work. Our first shot at this in a number of ways was Healthy Brain Network. So this, basically going after ages 5 to 21, multimodal characterizations, having a range of different data types, not simultaneous, but whether it's EEG, eye tracking, actigraphy, MRI, multimodal imaging, having that in the same subjects. And this here is an example of early on, this is with Simon Kelly, Nicholas Langer, and Lucas Parra. There's initial, the EEG protocol in Healthy Brain Network does use simultaneous eye tracking with EEG, and we've made thousands of data sets available using it. And Scott McKeague and Arlo Gorham are really doing an amazing job of actually reprocessing everything in the best, most optimal processing and making that publicly available. But these data sets, there's a whole range of challenges that I could tell you from just a data collection perspective. If anyone who worries about just eye tracking or just the EEG knows all the different challenges you can fall into with any one of these modalities. Then when you take two of them, put them together, and you try to scale it, the challenge grows. And that's its own learning process of how to do this and go through this, which the value of having an open data set is you get folks like Scott who reach out to you and say, did you see this with your data? Or have you thought about this? Or have you thought about that? Or you get folks in the community who say, hey, I found this artifact. You might not have seen this. And it creates admittedly, every time something like that happens, there's a part of me that my blood pressure goes through the roof. And then the other part is realizes the valuable part of that correction process. But one of the things that also has happened over the years is Scott has basically increasingly started to infect my mind with his vision about capturing naturalistic cognition and the whole MOBI idea of mobile body brain imaging, really starting to think through how do you get the many modalities at once? How do you really capture naturalistic cognition or behavior and cognition in this way that you get these highly multimodal recordings? And that's something that we've increasingly taken on in the new NKI-Rockland sample. So this is the NKI-Rockland sample 2. This data will start being released really in the next year or so. This is going to be, whereas the first NKI-Rockland was 1,000 subjects, ages 6 to 85, multimodal imaging, and then a very traditional looking deep phenotyping protocol with questionnaires. This one here, we have a whole new multimodal imaging protocol. We tried optimizing, and there's multi-band, multi-echo, there's a whole range of different kinds of imaging to put in there. But really, I think one of the most innovative pieces is taking the mobile brain body imaging, this MOBI idea, and working on trying to scale that. And so subjects who come in, we do get EDA, EKG, EMG, eye tracking. There's also motion capture, accelerometry. And we get this while they're doing a set of behavioral tasks. We put a significant focus on what some might say is a little more low level, because we're putting a focus on motor. With some parts are as simple as spiral drawing, but also handwriting. Here's an example of complex figure drawing, a classic neuropsych task like trails A, trails B, flanker. Here's a critical stability task. It's a vigilance task essentially. And what we're doing though is taking these tasks and capturing them with the MOBI framework. And that has definitely had its challenges, and we've gone through that process of reworking things and dealing with a number of the different challenges that come along the way. If this, let's see, is this where skip verification? Let's see. Okay, that's not going to play well, fortunately, with Zoom. But this here is an example of the handwriting tasks. So I'm going to skip playing it because I don't want to mess up the Zoom piece here. But why do we chase after handwriting in a sample that this is ages 9 to 75? Well, on the young end, we of course have things like ADHD, where we know you have differences associated with handwriting, and let alone thinking about dyslexia, discoordination disorders. And on the other hand, you have Parkinson's disease. One of the things that we did is the triple L's, the writing in cursive part, that actually has triple L's, panagrams and so forth, based upon this Parkinson's machine learning competition. And notice there again is spiral drawing. So as I was saying, the spiral drawing and complex figure drawing, those I found particularly exciting because of the fact that we're able to now, this becomes a machine learner's paradise. We're not just doing what's so often done in practice where here's an end result picture. Here, this is all implemented in a platform called MindLogger, where we're capturing, every single motion. So now the machine learning capability, questions alone jump out as far as prediction and what someone's, you could imagine when someone's making an error or not, or different kinds of strokes depending on the task, but also then having all this data so you can come up with fairly complex models and really explore brain behavior relationships, push boundaries on prediction. And the spirals I found particularly interesting because this work out of Columbia, where what they wound up showing is when you have folks do spiral drawing, you have subgroups that have very notable low amplitude fluctuations. And that to me, as someone comes from the ADHD literature, well, I think about those kinds of things going back to my work with Javier Castellanos, who's among the first to show that you have this periodicity in attentional lapses and so forth. And that was actually why we started championing resting state fMRI back then, is Javier noticed the similarity of the frequency of lapses in attention and what was in resting state fMRI with respect to being about 0.1 hertz or slightly lower. And the idea was that there's a biological mechanism deriving it, and that got him interested in that frequency range. But when we're looking at this here group is more associated with these phenomena, more associated with psychopathology. And these are low-level signals in some ways that, if analyzed appropriately, scaled and thought through, there could be incredible value for. Here's another study with spirals where you see essential tremor, cerebellar disease. I will have to say, as someone with an essential tremor, when I tried drawing a spiral, I looked a lot like this. And someone who a lot of people think is kind of ADHD, I also had a bit of this in my pattern, and I was like, could be chance. But the thing is, we will be able to figure out some of these leads, and we will be able to bring the level of analysis and characterization to another level with capturing data like this. But also, as Scott would point out, and one of the things that's trying to be addressed with frameworks like the HED is it's an incredible challenge to really characterize this data in its entirety and really see the full value of it, let alone deal with the technical challenges that one has to when pulling together the different streams, and which fortunately you have protocols like lab streaming layer trying to help bring the data together and more at the time of acquisition, rather than afterwards trying to post hoc a lot of things for even aligning the data. So these are, in my mind, incredibly promising avenues to go, and something that really, I think, is an inspiration, but these are also significant challenges. So I'm just going to finish up with a few more slides, just emphasizing everything I've spoken about currently was about being in the lab. But we know that right now we're looking at a time where going outside the lab, again, mobile phenotyping is where the field is going. And with great promise, the thought that from a mental health perspective, the thought that I could capture fluctuations over the course of a day or across days. Well, if you're talking about mood disorders, for example, incredible value in capturing that information and being able to characterize the variations that happen within and across days. So much of a signal in mental health in psychiatry is probably about the variation. And we think about that, 15 years ago, it was innovative to think about that in the course of an experiment, the variation. Now it's really about thinking about the variation over time in the real world. That's where so much of a signal is, and that's what we miss with laboratory measurements. So here's just an example of what actigraphy. This is data collected from a Healthy Brain Network, where you can get relatively reliable actigraphy data. You just need to have enough of it. And so here showing how many days goes in looking at inter-class correlation coefficients for just overall activity. And once you're sitting around 6 days, 7 days, your data becomes quite reliable. And you also have those real world challenges that come out, like finding differences in day of week with respect to reliability, because the patterns, our patterns will change depending on whether a weekend or a weekday. And we need to think about, it's a whole other set of challenges when we go into the real world and we lose those constraints of the lab. On the other hand, here's work by Kathleen Merrick-Hengis showing the value of combining EMA and actigraphy, so you could really start to understand how physical activity seems to be is a strong predictor of mood and interactions between physical activity, sleep, and energy. So the final point is, actually, this here is the ecologic momentary assessment protocol that was used as part of that study. This idea of being able to probe a person multiple times a day over multiple days or weeks, incredibly powerful. And I think this is where the field is going. Also, finally, cognitive assessments. The thought of taking some of those assessments from the lab and doing burst sampling. This is whether teams at WashU and MGH and others, there's a number of teams really starting to push that agenda. And I think that's incredibly valuable. It's something that we've been starting to do at NKI Rockland sample as well, whether it be you're trying to capture variations in performance as a function of day, or you just want to increase the reliability of your data by the amount you're able to collect across the multiple time points and days. Either agenda is a valuable one. Finally, we've been building a lot of the NKI, Rockland, and so forth into a platform referred to as MindLogger, open source platform that right now it's in a refactor phase. It'll come out of refactor at the end of April, and then there's actually a significant amount of scaling that will happen in MindLogger and Fusion of Biometrics. But this here is something where our vision is everything that we put in MindLogger would be questionnaires, surveys, EMA, cognition, so forth. You should be able to grab MindLogger and go and implement it in your own lab. So you have our protocols and everything that we do, and that's something that's the vision we're building off of. And we've also now are working with Alan and and his team in Montreal to start to integrate MindLogger with Loris so that it could serve as an instrument builder and really building that integration. Because I can tell you, I personally don't want to handle all this multimodal data and building all the behind, all that background infrastructure. And that's something where when we join forces between different efforts, I think there's incredible value. And finally, my last slide, I said at the beginning, is multimodal imaging the last missing ingredient? Let's say we've solved those reliability issues, we validate, we really figure out how to get the modalities, everything else. We're still not there. I think the ABCD study is teaching the imaging community the fact that epidemiology matters. And this is something also UK Biobank and other large scale efforts. We do need to then think about our sampling frame. And we need to think about who we're looking at and who we're making inferences based on. And there's appreciating the diversity in the neurobiology, and social determinants, and other factors. So that's, in my mind, probably the next major hurdle that we need to deal with. But this is where these digital technologies have incredible value, because you could design things as N-of-1 experiments, have scalable technologies that then you will inherently start to create these large-scale data sets as you scale them. And we can really appreciate that diversity more rapidly than what an imaging study would be able to, as much as I'm still an imager at heart. So, of course, many thanks to all the many folks that have contributed to this work. And that is it. Thank you for your time.
I'll get started. Yeah. You can go.
I can speak?
Yes.
Yes. As a tour de force across some of the more arcane aspects of the work that we do. Sometimes I think we forget how hard it is to do this. This is particularly relevant for the Global Brain Consortium, where we're dealing with sites all across the world, all of which have their issues with data acquisition and harmonization of their analytics. And I think what you saw from Mike is what often goes into deriving good discriminant results. So we have some questions which are beginning to appear. I'll just start off the discussion. Mike, what do you think is the most discriminant in child psychiatric diagnosis? Genetics, behavior, imaging? Do you have a sense of which one of these are more informative in making a diagnosis?
Right now, honestly, I would probably stick with behavior. I think we're able to use genetics and imaging to improve, but not in any real world fashion yet. I mean, with some exceptions. Some would argue autism has a subpopulation that, when you start talking about rare variants and so forth. But I think for the larger portion right now, behavior it does capture a very significant portion of the signal. We're showing these other methods can be used to improve. And I think that's great. But I always have the caution of right now, it's still, we need to do better than what we're doing clinically. And I don't think we're there yet. Though I will also say with behavior, there's just yesterday I was looking at someone was showing me machine learning applications to data, and basically saying if I look at an individual questionnaire versus subsets of questions from different questionnaires that you derive from machine learning, and showing that you can do better and optimize. But I think right now behavior still has the lead, and I think with the digital technologies we might really see behavior really take another set of jumps. But in the longer run, imaging versus genetics, that would be a hard one to call, because both fields are still maturing. But both fields also need to deal. I think that the targets need to still be better thought through. I think we get very caught up on, can you predict ADHD versus can you predict autism with imaging and genetics and those kinds of questions. And that probably will never work as well as we want it to, because of the fact that that those are not biologically defined diagnoses. Once we redefine the diagnoses, better appreciate the subtypes and so forth, from a biological perspective, they will do better. I think if the question is more about prediction of prognosis and outcome, there I think we see a lot more promise for where these methods will go in. And I think some of Connor Liston's work, where Connor was using TMS and basically predicting TMS outcomes with different connector types, I found that to be very promising. One of the other things is you're seeing more and more studies trying to create those links between imaging and genetics and going multimodal from that perspective. And those might really be the absolute most promising.
Okay. Thank you for that one, Michael. We have a question in the chat from Claudio Babiloni. Claudio, are you there?
Yes, thanks a lot for this fantastic lecture. My point is about the control of the level of vigilance or consciousness of the participant to an EEG or neuroimaging, functional neuroimaging experiment, due to the fact that during the resting state, for example, you can have some transition to drowsiness or light sleep, even during 15 or 20 minutes. And then the possibility that in the morning, the participant can have some stress and come to the experiment.
Data will give you a significant amount of insight into whether someone's in tune, internally or externally directed moment of attention, what levels of arousal. Obviously, having EEG with fMRI helps as well. The multimodal gives you that more definitive picture. And yeah, I think it's a challenging problem that the literature is not yet figured out how to fully handle. And even when the literature is handling it, I don't think folks fully acknowledge it. It depends on who you're speaking to, but it's become much more a focus in the resting state community than what it was 5-10 years ago. And the multimodal characterization will help us through that.
Okay, we have a question from Pedro.
Well, actually, it's two questions. I'm going to pack it in. First, the first question is that I'd like to comment, Mike, on how we can control the quality of the data. This is becoming more and more, as we have more data, which is good. This is a big problem. And as you know, for example, we nearly have published, one of the people who are here, looking at your data set, how good are the, let's say, the lead fields to do source localization. And we had to come up with rather innovative methods to be able to go through thousands of MRIs and check the final quality. So that's the first thing. How do you see this? The second one is that in multimodal combinations, you have two ways to do it. One is purely data-driven, using machine learning methods, and now we have artificial intelligence. There's another, which is a model-driven approach. And with the amount of data we have, I don't see very much work on the model-driven approach, though we're seeing some things like what's happening in the virtual brain. What do you think of this possible contribution to multimodality? So it's two questions.
Yeah, the first one keeps me up at night. The second one is just one of those, I think, intellectual challenges as to which way to go or find your complementarity. So the first one I'll start with. I think we need to think of purpose. Like, I know right now for some of the work that we've been thinking through with a global center that we've been starting, when I'm thinking about having something like a MOBI set up at a site someplace else in the world that may not have spent this amount of time trying to figure out how to optimize it, we've been starting to look at, well, okay, what can you do with more lightweight setups? So, the different EEG setups that whether it be a motive or something along those lines, how far can you push things which feel like they have lower barriers of entry, but you then have to accept the limitations of the data. So on the one hand, I guess the point is, you can figure out what's that minimal data that I need depending on my purpose and try to generate best practices for that. When it comes to the higher quality data and the kind of stuff that we would want teams like your team, Scott's team, and others to really be dealing with, I think that's the part is this, honestly, this collaborative interactive loop. It's helpful when we hear from teams, hey, wait a second, here's what we're seeing. And that's where collaborating, coming together to figure out how to improve the acquisition with best knowledge. And then I do think that there needs to be a lot more focus on establishing best practices. I think folks need guidance, and we need to bring down the barriers of entry. That's challenging because a lot of this work it tends to be more niche and done in smaller subsets. And you know, as we step into multimodal, we have to always be humble about the fact that I might know what's best in my domain, but I don't know what's best in yours. So when I get a phone call from anyone and they're saying, wait, I see this or that in your data and here's how we can prove it, it doesn't make one happy, but at the same time, it's like, okay, let's do this. And I think we need to, right now, fields are increasingly thinking about standards within the fields, but we need to get more connectivity essentially between different domains. That's part of what we're trying to do with the NMind front as an example, is really start to get folks looking and really figuring out why do we have all this redundancy and duplication, and also why are there all these gaps in communication. But that I don't know of a great other way to do it other than to sit there and always look at what are we trying to accomplish? What's the minimum standard or best practice for obtaining data for that? Otherwise, the more the technology improves and data acquisition setups get easier and so forth, then that's great. I know at NKI, we were suffering with using a gel-based caps. And although I didn't want to use the EEGI system like what we have in Healthy Brain Network, and then actually Eduardo wound up pointing out to us that Brain Products had a saline cap that we could use, and that brought setup time from 45 minutes down to 15 minutes, and the data, data quality is good, and we were very happy. It's a matter of really looking through and figuring out what's most optimal. And I know actually Arnold Delorme had a paper he shared with me that him and Scott and others had put together, looking at the many different systems available, and and helping identify some of the differences. We've been doing some of our own in-house testing for some of these lightweight systems and looking at where can we benchmarking them against each other and start to try to get an idea of what some of the signals look like. So I think that process has to happen, has to become more collaborative, and there needs to be more guidance from folks who can look across the communities and pull pieces together. The other piece, data-driven versus more model and principle, with that, I always try to view them as complementary. My thing is, if basically, I used to put a slide up where I took the Serenity Prayer and basically had something along the lines of test the hypotheses you know, explore for ones you don't to know the difference. And basically, it is that style model, but we also have to be careful because the challenge of exploratory is you can find a lot of things for reasons you don't actually understand. And if you're going to start with something from machine learning or so forth, and you find some pattern, you need to explain it, or you want to explain it. You should at least truly establish reproducibility, but I think it should be guiding future hypotheses. And that's kind of how I view the interplay. It's really use the exploratory approaches to guide more model or principle-based approaches. As far as how much to constrain ourselves with different biophysical models, I mean, we need to also be careful because the biophysical models also have a number of assumptions in them that may or may not be accurate. So it's a little tricky, but I do think there's a balance there that can be had.
Okay. We do have more questions in the chat, and but I think given the time, we probably should close this session. Mike, perhaps you could answer those questions in the chat if you're not completely exhausted. And I'd like to thank again Michael for this stimulating and wonderful tour de force. I'd also like again to thank the Mortimer and Vera Gross Foundation for making this possible. So everybody, we're going to take a short break now, and then we'll reconvene. We have 3 breakout sessions for about 2 hours from 10:30 till 12:30, and then we'll reconvene tomorrow. So thank you very much, everybody. I look forward to continued stimulating discussions amongst us all. Bye-bye.